the talk.
So thank you for the invitation. It's a pleasure to be here. So my talk will be on random concave functions on an equilateral lattice with periodic hessians. So the following questions are relevant to machine learning. You have a class of functions. So for example, you may be interested in fitting Lipschitz functions to data. In a Bayesian setting, you would have a measure over the space of Lipschitz functions, and which would be a prior measure. And then as observations arrive, you would improve your estimate of what the actual underlying function from which observations are drawn is by some sort of Bayes rule. But in order to give the right amount of weightage to the observations and the prior, one has to understand the priors, the way the priors behave in a function class. So this is so this question of understanding whether typical functions from a distribution concentrate about their mean or not is of relevance in Bayesian statistics. And in general, it is also of importance in machine learning when you look at questions related to generalization error. So the prior distribution will depend on the specific application, but today I want to talk about one particular one, which is random concave functions on a large equilateral lattice. So we'll be looking at so we'll be looking at triangular lattices and random concave functions where the Hessian is constrained to be periodic with a certain average value. So so this comes up in it's related to statistical physics, because if you take a random concave function on a equilateral lattice and you measure the gradients on the faces, or rather the little triangles that make up the open sets, between the interstices, those gradients form the vertices of what's called a honeycomb. And these are all hexagons. The lengths of the sides are variable, but the angles are all 120 degrees. And these come up when you want to model large planar molecules with atoms of different sizes, for example. And there is a variant of this where if you look at integer valued concave functions, then in fact they are in correspondence with square triangle tilings of the plane. So I'm only going to talk about the real variant today. But so there is also a connection to representation theory. If you look at the integer valued concave functions on an equilateral lattice on a fixed triangle with given boundary conditions, the number of such concave extensions is what's called a Littlewood-Richardson coefficient. This is a Klebsch-Gordon coefficient, which appears in physics as well. So what happens is, if you take the tensor product of two irreducible representations of the general linear group, you can decompose it as a direct sum of irreducible representations. And the multiplicity with which a given representation occurs is given by this Littlewood-Richardson coefficient. And that is also has a combinatorial description as the number of concave extensions of a certain picture to the interior. So the next slide will clarify this. So here we have lambda equal to 40, 30, 20, 10, mu equal to 40, 30, 20, 10, nu equal to 65, 55, 45, 35. So these are the indices which parameterize these irreducible representations. So V lambda is one irreducible representation. And you're interested in basically some sort of decomposition rule of this sort and how many times this object appears in the direct sum decomposition. So what you do is you take this triangle and you write in increasing order 0, then 40 because 40 is here, then you add 30 because 30 is here, add 20 because 20 is here, add 10, and you get numbers 40, 70, 90, and 100. Then you go down, you add mu. So you add 40, you get 140, you add 30, you get 170, add 20, you get 190, add 10, you get 200. And lastly, for the last side, you put nu. So nu is 65, 55, 45, 35. And now you have these boundary values and you ask how many ways are there to write integers on these places. so that when I take the piecewise linear extension to the entire triangle, I get a concave surface. And this is the Littlewood-Richardson coefficient. So here example is one valid filling. So I put 125 here, 100 here, 150 here, and you find that all the constraints are properly satisfied. So these constraints are called rhombus constraints because in order for this to be a concave extension, it's good enough that every rhombus over here is has a certain inequality. Basically, the average of these two is greater or equal to the average of these two. And this is true for every rhombus. So the average of the larger side, larger diagonal is less or equal to the average of the smaller diagonal. So in this rhombus, for example, you have y plus w greater or equal to x plus z. So if you have these constraints everywhere, you're guaranteed that the thing is concave. And similarly, if you have a concave surface, these will be satisfied. So the set of all possible extensions form a polytope in some roughly n squared dimensional space, where n is the side length. So there's also a surprising connection to random matrices, and the volumes of these polytopes that I just described have an interpretation as the probability density of obtaining a Hermitian matrix with spectrum mu when two Haar random Hermitian matrices with spectrum lambda and mu are added. So this is a result of Knudsen and Tau. This came from something called the saturation conjecture, but then they have several results also related to the real hives. So the saturation conjecture is something related to the integer hives. So for all these reasons, it's of interest to study these random concave functions. And we are interested in this situation when these hives are becoming very large. So you want to know that if you have two very large Hermitian matrices with given spectra, what's the probability density that when you add them, you get a certain spectrum. Yeah. That's right. So the boundaries here are fixed by external data, but you just want to write numbers on the interior vertices. That's right. That's right. So this is that number, the number of possible ways of writing integers with all these rhombus constraints satisfied. But we'll be interested primarily in the case when you're allowed to write real numbers here, and then we'll look at the volume of the polytope and stuff like that. So this is the number of integer points in a certain polytope. We'll be interested mostly in the volume of that polytope, Lebesgue measure. So because for this reason, the connection to random matrices. So we would like to make these matrices very large and understand some properties of these polytopes when for example, when these side lengths are sampled from some distribution. So in free probability, one does things like takes two Haar random matrices of very large size, adds them, and there's a result which says that the spectrum of the sum converges in some sense to a fixed spectrum. So this is related to that, although this has a lot more information in some sense than just the convergence, because this is talking about even very unlikely mu's. It gives information about even very unlikely mu's because of the volume of this polytope. Okay, so we'll be interested in looking at these very large triangles, but in the scaling limit literature, the first step to understanding such questions is to consider simpler boundary conditions. In our case, these are periodic boundary conditions. In our case, we'll be looking at the situation when the Hessian is periodic. So what does it mean by the Hessian is periodic? So recall that we had those rhombus inequalities for a rhombus. We want that function, which is a real number associated with every rhombus, to be periodic with some large period on this lattice. So you have all these constraints. You have one constraint for this kind of a rhombus, one constraint for this kind of a rhombus, one constraint for this kind of a rhombus. But you could shift this by some large n, where this side is 1, you shift it by n, And what you are enforcing is that the value of the Hessian, that is this number, b plus d minus a minus c, is exactly the same for this, and it's translate by n times the side length of one rhombus. So this actually takes what is otherwise an infinite dimensional polytope, it turns it into a finite dimensional polytope, because now the number of dimensions, which is the number of parameters, is only finite. It corresponds to the fundamental, domain of this translation group. So we'll fix the average Hessian to be something, and then ask whether a random concave function with this average Hessian uh, behaves like a fixed, like converges in some suitable sense to a fixed concave function or not. So that's the question we'll primarily be interested in. So here is that large rhombus, and for every such little rhombus, the value assigned is the same as its translate by n times vector u and n times vector v. Okay. So we'll be interested in this. N is going to tend to infinity, and the average Hessian is some fixed number. The first observation is that the polytope that you get when you give these periodic boundary conditions has a L infinity diameter of that is bounded below by n squared. So how can you see this? You can see this, for example, by just taking a quadratic function with the right Hessian, and then taking some polyhedral thing with faces that are flat. So that thing, the polyhedral thing looks like this, and the quadratic thing looks like this. And as the mesh size becomes smaller, or as we are doing it, we are allowing the minimum length scale to be 1 and letting the period tend to infinity. But for this picture, let's suppose we are making the mesh finer and finer. Then when you have a quadratic function with a fixed Hessian, and if that Hessian is supposed to be fixed at a scale of 1 by n, then the height has to so the Hessian essentially has in the denominator the area of the rhombus, and that goes as 1 by n squared. So you get a n squared over there. So it's not difficult to see. So you know that in terms of the diameter, these polytopes are actually not getting squeezed to a point. But our main result is that if you have certain conditions on the Hessian, namely that the slacks of those rhombi are S1 equal to S2 and less or equal to S3, then a random Hessian actually does not look like this polyhedral Hessian at all. A random concave function does not look like this polyhedral concave function at all. It looks very close to this quadratic function. So that is the main result. So you have some sort of concentration, and the slack was that b plus d minus a minus c. So this is some, yeah. So when you have a polytope, so if you have a polytope with constraints, generally you have this is the origin. The slack is the distance to the constraint. That's right. There's a translation involved. So in the polytope language, this is the slack. But if you look at what a certain point, so if this point had been not origin but some point x, which actually corresponds to a concave function, then it would this direction represents a point, or rather a rhombus. Let's see. So this face represents a rhombus, and the distance to this point represents the Hessian evaluated on this rhombus. So the periodic condition is that so we are actually looking at an infinite concave function, but it has the property that if you look at the Hessian at a small rhombus here, and you shift that rhombus by a lattice vector, which is n times u or n times v or some integer convex combination of these, you get exactly the same Hessian. So in other words, another way of saying this is that if I translate this whole picture by one of these vectors, I'm effectively just adding a affine function. These are equivalent. So this is so in the language of convex geometry, this is what we are saying. So if you want to represent a high-dimensional convex set in a plane, people often do this because you want to represent the mass versus the distance trade-off, and this is how that looks. So it doesn't look convex because much of the mass is in these long tentacles, which are rather far away from the origin, and you can't represent this effectively on a plane. But so think of this as the polytope, which has got a large diameter of Cn squared. However, the mass is largely concentrated inside a very small square of a very small cube of side length epsilon n square. This epsilon can be arbitrarily small, but as long as I let n tend to infinity, the 1 minus little o 1 of the mass will lie inside this square, this cube. So our strategy is going to be to define a family of polytopes whose total volume is little o of the volume of these periodic hives, such that for every point in the complement of the cube, of that tiny epsilon length cube, epsilon n squared length cube, there is a polytope that contains this point. Okay, so this is the strategy. You have this polytope, you have this cube. We don't care about the cube because we just want to show that most points are inside. But we want to cover every point in these tentacles by a convex polytope, such that the total mass of all these convex polytopes divided by the mass of this Pn of S is little o1. So that will ensure that most of the mass is inside this because everything else has been covered by a small total Lebesgue mass set. Okay, so I'll outline the case when the Hessian is all equal to 2. So the scaling, there's some scale invariance. You can just multiply everything by a scalar and nothing really changes. However, different Hessians do behave differently because of lattice effects. So as I said in the original main theorem, the main theorem holds in somewhat more general setting of S1 equal to S2 less or equal to S3. So this is one special case where the proof is somewhat simpler. So I'll only go through this. So now we are dealing with zero mean functions on a discrete n cross n torus. I've taken that rhombus and pasted the sides together because when I shift by a certain amount, I'm getting exactly the same value of the Hessian. So I'm thinking of the Hessian as a function on the discrete torus now. So these are mean zero functions on a discrete torus, and the Hessian at every rhombus is bounded above by 2. Recall that earlier these are concave, so they were bounded above by 0, but now I'm subtracting a particular quadratic hive. So while a typical thing might look like this guy, I'm now subtracting this quadratic hive from everything, and so what I'm getting is some function that looks like this, roughly speaking. I'm doing this because otherwise I won't be able to deal with functions on the torus. So now we're talking about some function that looks like this with a upper bound on the Hessian of that is 2 and no lower bound on the Hessian, right? So the Hessian can be as small as possible. So in this point, for example, the Hessian is very small. So we wish to show that the L infinity norm of a random function in this translated polytope is less than epsilon n squared with probability at least 1 minus little o1. It can be negative. So Hessian is a matrix, and when I talk about Hessian, it's a triple. It consists of the values on the 3 different kinds of rhombi. The Hessian is negative if that B plus D minus A minus C is negative. That's about it. The Hessian, I'm allowing it to go as low as possible. Yeah. There is no negative constraint. There is in fact going to be a constraint due to the fact that it's mean 0 and everywhere else the Hessian is bounded above. So it cannot therefore go to minus infinity, but it will be something that as a function of the side length L, n, which is also tending to infinity. So the main tool is that of the Minkowski inequality. So what this says is that if you have two convex sets, it's actually more general than this, but we'll care about the case when K and L are convex. Take two convex sets, look at the Minkowski sum. So here is a convex set K, the green is a convex set L. We are adding L to K. In our setting, actually, this will be L and the green thing will be K. So you think of adding k to L, and you get this set, gray set, which is the union of everything. So this gray union green union purple consists of points which can be expressed as the sum of a point in this purple thing and a point in this green thing. So this green thing should be somewhere here. It's not visible, but it should be somewhere here. Okay, so basically the set of all points of the form x plus y, x belongs to k, y belongs to L. So Minkowski inequality says that if you raise it to 1 by m, m being the dimension of k and L, then this inequality holds. So we'll be using something closely related to this. It's called the anisotropic surface area. So when you take the normal surface area of a convex set, for example, what you normally do is you add a small ball, a Euclidean ball, and you see how much the volume increases. Now we won't be adding Euclidean balls because we're interested in something different. We'll be adding polytopes. Okay, so this is going to be when you do that, you get this anisotropic surface area where essentially you grow the convex set in different directions by different amounts.
Isn't that called mixed volume?
This is a special case perhaps of mixed volume, yeah.
And then the inequality is the Alexander function.
That's right, yeah. That's right. Yeah. Yeah, so this is this anisotropic surface area, and this is greater or equal to m times k to the 1 by m, L to the m minus 1 by m. We do some simple manipulations and write this as the relative volume of k with respect to L being less or equal to something raised to m, where this is the anisotropic surface area. So one thing one observes already is that if you get minor improvements, like good, if you get reasonably good upper bounds on SKL, this is dramatically sort of it gets boosted up because you get it's all raised to this very high power. So this is what is going to help us. So this is basically how we control the volumes of those polytopes I'm going to use to cover the tentacles. So in this process, one needs to understand the limiting behavior of the volume of these hive polytopes raised to 1 by n squared minus 1, where n squared minus 1 is the dimension. So a lower bound of 1 follows from some basic facts like this unit ball is always contained inside Pn of S, unit L infinity ball, so the small cube. And because we are looking at mean zero functions, you end up having a section of this cube being contained in Pn of S. But Waller has shown that any central section of the unit cube has volume at least 1. And so you get a lower bound of 1 on the volume. And a more involved argument using differential entropy shows that the lim sup of this quantity that we care about is less or equal to 2e. So it doesn't grow too high either. And however, so you have the lim inf being greater than 1 and the lim sup less than 2e, less or equal to 2e. But there is some kind of approximate monotonic increase in the, this is like the entropy per vertex of the random function. It's not exactly that because I've not taken the log, but if I'd taken the log, it would basically be the differential entropy per vertex of the random concave function. So this is, it turns out to be approximately monotonically increasing. One can prove this. And then if you have a monotonically increasing function, a sequence with upper and lower bounds, you know that it has a limit. So essentially that shows that this quantity does get a limit. And but we don't know what the limit is. It would be of very much interest to know it's the limit as a function of S. But as of now, we only know that it lies between 1 and 2e. So now, so we want to show that the L infinity norm of a random function in the translated polytope PNS is less than epsilon n squared with a large probability. So what we'll do is we will want to look at small areas of this random function. By small, I mean small compared to n. They're still going to be of the order of some epsilon 1 times n. So they're actually very large. But if you look at them as a ratio with n, then they are small. Okay, so X is a fixed hive. Delta is going to be the Laplacian on the discrete torus. This is an averaging operator. It takes this rhombus of side length n2 equal to epsilon 1 n and just convolves it with the uniform measure on this discrete torus of discrete rhombus, if you like, of size n1. This size n2, which is equal to roughly epsilon 1 times n. So phi is the indicator of this, and you're dividing it so that it has unit n1 L1 norm. So it's you multiply it by n1 to the minus 2. So then we look at this convolution operator. It's a smoothing operator. There's a Laplacian also, and it's now applied to the hive. If you just took a smoothing operator, applied it to a hive, you get another hive, which is somehow much closer to being quadratic because you've averaged it out nicely, but it's still not quadratic. But now you're applying the Laplacian, which is not a smoothing operator. It actually enhances the high frequencies. So what we have as a lemma is that if you start with a function that deviates from being this quadratic, recall that in this picture now it's not a quadratic we're talking about, it's a plane thing we're talking about. So everything that here has been translated to this picture by subtracting this quadratic picture, and we are talking about functions of this form which we want to show are very close to being flat. Okay, so if the L infinity norm is more than epsilon n squared, then the lemma says that this operation gives you something with a large L2 norm. Okay, so this is the rhombus of size n2. I've made it a square for simplicity rather, and so this is the Laplacian. It takes a point and it's like a mask which evaluates the function on the boundary, subtracts 6 times the value here, and that's the Laplacian. So, and this is the indicator of this divided by n1 squared. That's phi. Okay, so this was that. This is fixing a point here. Delta is the Laplacian on the discrete torus. This box is a rhombus of size n2, and phi is basically the indicator of this box divided by n1 squared. So the lemma is that if the L infinity norm of this thing is big, then the L2 norm of this convolution is also somewhat large. And how does the proof go? So because of the one-sided bound on the Hessian of x, phi star x is bounded below by omega epsilon squared n to the 3. So basically what happens is, while this function can somehow have a very small Hessian, it can't have a large Hessian. So what that means is that if at some point you have a big derivative, then the only way of recovering from this is to sort of go very slowly. Sorry. So it's to go very slowly upward, and you have this large arc basically. There's no way of just recovering quickly from something like this. So because of these things, you end up incurring some L2 norm, and you incur this L2 norm, and then if you have something with a large L2 norm and you apply the Laplacian on it, you are not going to do much better than the smallest eigenfunction of the Laplacian, which in this case is 1 by n squared up to some sign. So you lose that additional 1 by n squared, and this is a so this thing actually, let's see. Yeah, so I mean, in the end, what happens is you see that this has to be at least epsilon squared n. So this 1 by n squared gets multiplied by n cubed, and you get epsilon squared n. Okay, so now here's where the convex geometry comes in. So we want to now relate this picture involving some operations on these hives to the geometry, which is high dimensional geometry. So what we want to say is that somehow the functions which vary a bit are unlikely, like their neighborhoods do not carry much mass because of the variation. But this variation has to be some large scale variation, for deviation from the average Hessian. Okay, so basically it turns out that this SKL by ML, this quantity is going to be pretty close to that phi star delta star x when you choose k appropriately. Okay, so we already know this bound, and this quantity gets related to that thing which we have already some bounds on. Okay, so what is k now? So k cannot be the whole thing, because then everything will average out and you will get nothing. But what you do is you kind of focus on these bad pieces. So you know that if it is oscillating, if this thing is oscillating at a large scale, there are some patches where the average Hessian looks significantly different from what it should. And you focus on those patches and kind of project onto just those coordinates, and you'll get something which basically means you restrict your convex surface to those coordinates. That's like a projection in high dimensional space. And you will notice that the geometry is a bit different from what you expect the geometry to be if you had a constant this thing. So what we're doing is we are isolating one piece like this and just restricting the attention to this piece. Okay, so that's a projection in terms of the geometry of the polytopes. Okay, so then if this is chosen in the right way, then it turns out that an isotropic surface area normalized is rather close to this expression. You take this to the 1 by n. We have already seen that this is less or equal to this by Minkowski or some variant thereof, and this becomes approximately less or equal to this quantity because this is very small. Now we have this, you take logs. When you take logs, this inequality always holds. So when you take logs, you get that this thing is less or equal to whatever you get when you substitute this. However, this quantity has to be controlled somewhat carefully, because if this becomes too big, then the whole thing becomes useless. So this has not to be too big. And it turns out that with some slight argument, you can show that this is not too big. It is, in fact, it is independent of n. It just it's large because epsilon 1 is itself tending to 0, but it's not that large because we're looking at fixed epsilon, n tending to infinity. Okay, so we have this, and now these terms, because so these terms, because this is a mean zero value now, we have removed the quadratic that we expect to be the mean. This is mean zero. This is so this is also, phi is an averaging operator, so phi star x is also mean zero. Now we are taking the Laplacian of this, and we are summing over all O, I, and j. So this is effectively like integrating this over the entire torus, and that one can see is rather close to 0. Nothing here is exact because there are some boundary effects, but one can control these. So the thing that remains is this, and this is a negative term. So what we get is that the log of this is less or equal to something that is strictly negative, and with some value that we can get our hands on. So what are these polytopes we are going to use to cover? The polytopes we are going to use to cover are those polytopes that you get when you take a projection of this Pn of S onto the boundary values. So recall that we had this picture of a rhombus. And these double layer boundary conditions, right? So this is going to be one piece. So we're going to essentially fix 2 layers of the boundary everywhere. You need to fix 2 layers of the boundary because this Hessian is a second order operator, and if you just fix one layer, you can still have interactions between the nodes on this side and this side. But if you fix a double layer, then these are completely decoupled. Everything here is completely decoupled from everything here. So you get these smaller pictures basically, which are pasted together at the boundary. But when you condition on the boundary, you have effectively decoupled everything. So that's what we are doing here. You're conditioning on the boundary to be some value, and you're taking a projection which just notes the values inside. So that's the polytope that we're going to use to cover. So in other words, for every set of boundary values, you're going to get one polytope, and that polytope will be used in the cover. Okay, so the main polytope, as you can imagine, is somewhat approximately less or equal to the product of the projections. So I don't want to go into this in too much detail, but basically it's like looks like a cube, and the volume of this cube is less or equal to the product of the projections. And we already have this inequality. So this leads to the existence, this is over offset. So I drew this with the offset 0, but I can translate everything because it's a torus. And it leads to the existence of some offset such that you get this bound on PO that is less or equal to e to the minus omega m epsilon to the 4. And this is essentially the volume of the Pn of S. Okay, so this gives us this bound, but the total number of polytopes is only some n to the theta n by epsilon 1, because we are only noting down the values very close to the on a very small number of nodes, relatively speaking. So in entropy terms, you're fixing very few of these nodes, so they don't really affect the overall entropy. And so the number of these polytopes is very small. It has an n in the exponent rather than an n squared. Okay. And so the overall intuition is that why do we expect a random concave function of the periodic Hessian to be close to quadratic? So suppose the function has a Hessian that deviates in a systematic way from S over large regions, then the resulting large-scale variation in the Hessian, together with something like the strict concavity of entropy. Again, this would be of interest to prove rigorously, but we don't have a proof that the entropy is strictly concave. We therefore had to use all these anisotropic surface areas, some sort of surrogate for this. And this ought to make the measure of an epsilon neighborhood of F small. So basically what happens is when you instead of having something that is flat, you have something that goes up and goes down. These portions have more entropy because there is no lower bound on the Hessian. So you can oscillate more basically. But these portions have less entropy because there is already a constraint that says that the Hessian is bounded above by 2. So, and this is already coming rather close to 2. So the amount of variation in these portions is less. But the amount that you gain by having this is actually smaller than the amount you lose by having this due to this something like the strict concavity of entropy. And that's why these sort of things get penalized and you end up with something that is more or less flat. So these are some questions for the future. So what about other periodic boundary conditions? So we have only looked at some periodic boundary conditions. And what is the shape of a random hive chosen uniformly from this Dirichlet boundary value question, where all the vertices are in the boundary are fixed? So this was sort of the original motivation. Okay, and so thank you.